All right, now we're going to start to get a little more analytical with our study of dynamics. These slides are from Chapter 1, Section 2, and we're going to start to lay some of the groundwork that we'll need to solve a variety of dynamics problems. So the objectives here are just review some of the basic geometrical and physical concepts we're going to use for the rest of the semester and then you'll use throughout your career. So a couple of very basic ones, space and time. Space is defined for us in terms of a Cartesian coordinate system, at least for the most part. So XYZ coordinate system uses the right hand rule, all the usual stuff. We have some point P. A point P usually has a mass but has no volume, right? So it's just a point particle and it can move, it can translate in the X, Y, and Z directions, but we don't have to worry about any kinds of rotations or anything like that. And time, I don't have to explain to you what time is in this context. We'll be talking about forces. Again, those are pretty intuitive. You apply forces to objects, they move. If we know the forces on an object, as I said in the last video, then you can analyze its acceleration and therefore velocity and position given the right inputs. All right. The mass of an object is a measure of the amount of matter in it, and so we'll use that uh, pretty much for every problem we do for the rest of the semester. Some of the forces on an object is the mass times acceleration, so we need it every time we solve a problem like that. And then inertia is a body's resistance to a change in its state of motion. Moving objects like to say moving, that sort of thing. And so um, with these three concepts, we'll be able to begin solving problems. As I said, a particle is a point object. It has mass, but we don't have to worry about rotations and that sort of thing. Okay, so most of the early work we'll do deals with these particles, and they're just points in space, and they can translate around, and we'll study that. Later on, we'll give a body some volume, and then look at rotations of that body. But that'll come later in the semester. We're going to use vectors a lot in this class. So in this class, a vector is denoted by a letter with an arrow over it. So for example, this letter M with an arrow over it, that's a vector. There's a force vector. Alpha is a rotational acceleration. A is a linear acceleration. So all these things with arrows over them are vectors. Something without a vector is a scalar. It's just a number, but it has no direction. Unit vectors have hats, so you see this I and j down here. I is typically the unit vector in the x direction, so it's of unit length, but it has direction along the x, uh, along parallel to the x direction, at least in this case. And j is a unit vector, has unit length in the y direction. If they have double arrows like this and this and this, they usually deal with rotation. So like omega would be a rotational velocity. It's the rate at which something's spinning. M is a moment, it's like a twisting force, and alpha is a rotational acceleration. So that's basically the conventions we'll use to do vectors in this class. All right. So in a Cartesian coordinate system, we'll represent vectors as arrows. Here's an XY 2D Cartesian coordinate plane. We'll use the convention that the vector r sub p slash o is the position of p relative to the origin O, right? So it's the position, it's a vector representing the position of point P relative to, in this case, the origin. So here's the origin, here's point P. The rp slash O is just this arrow right here. It's this vector represented by that arrow. Okay. That vector has a component in the x direction and a component in the y direction. We'll call those rx and ry. And we can represent r as rx times the unit vector in the x direction plus ry times the unit vector in the j direction, or in the y direction, which is j. So rx and ry are scalars. They're the magnitude, essentially these distances right here. They have no direction, and then we multiply by the unit vectors to scale them up. From basic trig, the magnitude of this, that is Rx, is the magnitude of this, which is the magnitude of the r vector times the cosine of the angle between them. And ry then is the magnitude of r times the sine of the angle between them. And so we can write for the position of, say, point A relative to B as the x position of A minus the x position of B, or this distance here, times the unit vector in the I direction, in the x direction, plus this distance here, which is ya minus yb, times j hat, which is the unit vector in the y direction. So there's a number of operations we can do. If you multiply a vector by a scalar, you just multiply the components by the scalar a. To add vectors, you just add the components. So r plus w is the x component of r plus the x component of w times the I hat plus ry plus wy times j hat. You can take dot products. The r dot w is the magnitude of r times the magnitude of w, so the magnitude of the two vectors times the cosine of the angle between them, and you can use those to find projections of one vector along another. And then there's cross products. If we take vector r, cross it with vector w, it's the product of the magnitudes times the sine of the angle between them, and the direction is perpendicular to the plane formed by the two vectors that we started with, and it uses the right-hand rule to figure out the direction, right? So if you point your fingers at r and wrap them in the direction of w, your thumb will be pointing in the direction of the cross product. The magnitude of r is the square root of the sum of the squares of the x and y components. The direction of r, or the angle in the xy coordinate system, is the inverse tangent of the y component divided by the x component. That is, the tangent of this angle is this height minus this horizontal distance, or divided by this horizontal distance. And we can also denote the vector as its magnitude times a unit vector in the r direction, right? So we can define ur as a unit vector in this r direction, and multiply by the magnitude of r to get the r vector. All right, and ur can be written as the cosine of the angle between r and the x direction times the unit vector in the x direction plus the sine of that angle times the unit vector in the y direction. Quick tip: if I have a vector in a unit vector in the one direction and a unit vector in the two direction, and I have some vector q in that plane, then q dot q1, that is the projection of q along the one axis, is q dot the unit vector in that direction, which is the magnitude of q times the magnitude of u1 times the cosine of the angle between the one direction and that q vector. And since u1 is had as a unit vector, then that has magnitude of 1. So the projection of the q vector along the one axis, that is the component in the one direction, is the magnitude of q times the cosine of the angle between q and the one direction. All right, I'll skip this for now. If you really want to see this, it's in the text, but I don't think we'll need it this semester. A little bit about units. Okay, there's two main sets of units we'll use in the class. One is the US or British set of units, and one is the SI units. Okay, for forces, the US is pounds and the SI is newtons. Okay, and Newton is a kilogram meter per second squared. Kilogram times a meter per second squared, right? A mass times acceleration, essentially. Mass is slugs in the British system, which is equivalent to a pound second squared per foot. And the SI is kilogram. Length is either feet or meters. Time is seconds in both cases. Okay, we recommend you just use one system or the other, not mix them. If you mix them, it just leaves you susceptible to making silly errors. Okay, so try to use one system and stick with it. So I want to just work out a few examples, first dealing with vectors and then dealing with masses. So in this example, we take a map of Minnesota and we lay out an origin in the lower left corner, and then we identify the cities Minneapolis, Duluth, International Falls, and Fargo-Moorhead. And we're going to answer these 4 questions based on this map. Okay, so first of all, what's the position of Duluth relative to Minneapolis? Right, so there'll be some vector between the two. We can write down the x component of that vector and the y component. We can get that position. Then what's the orientation relative to north of the position of International Falls compared to Fargo-Moorhead? And really we're looking at the vertical component there of the vector between them. Then what are the scalar components in the east and north directions of the position of Fargo-Moorhead relative to Minneapolis-St. Paul? Again, you draw a vector from Minneapolis-St. Paul to Fargo-Moorhead, and then you give the eastern or x and northern or y components of those vectors. And finally, you find a position halfway between Minneapolis and International Falls, right about here, and find the position of that point. That is, you draw a vector from the origin to that midpoint and then find the components of that position. Okay, here, just so you know, are the cities, the locations of those 4 cities in east and north components relative to this origin down here in the corner. Okay, so based on this information, we can answer those 4 questions. So the first one is what is the coordinates of D relative to M, right? So Duluth is here, Minneapolis is here, so we can write down the vector between them, RD/M, as the difference between RD and RM, right? So RM is the vector from the origin to M. RD is the vector from here to Duluth. And that relative vector is this one, right? It's the difference in the x components, right? So the x component of this vector is just the difference in the x positions of D and M. So it's 259 minus 216. And then that's the x component, and the y component is the distance here, which is yd minus ym, which is 267 minus 130. So we get a vector representing this relative vector of 43 in the x direction plus 137 in the y direction, and these are in miles. The magnitude of that is 144 miles, and it's 72.6 degrees from the x-axis. Okay. Part B is determine the orientation of I relative to F. So I is up here, F is here, so there's a vector from F to I. You know, again, we want the x and y components of that vector. If we just want the orientation, all we need is the angle of that relative vector to the x-axis. So we can write down that the unit vector is the r vector divided by the magnitude of r. And the r vector is the difference in x between I and f, 195 minus 12. Right? So since f is almost on the y-axis, its x value is small. And then the difference in the y values, it's 413 minus 278. That's this vertical distance here. And then you divide by the magnitude, and you get 0.805i plus 0.594j. So those are the xy coordinates of this vector between f and I. To get the angle, we take the inverse tangent of the x component divided by the y component, and we get 53.6 degrees. All right, part C is find the east and north components of R for F relative to M. F is here, M is here. So we draw a vector from here to here. So we should get a negative x component and a positive y component. So the x is just the difference in the x values. Okay, so 12 minus 216, and the y vector is the difference in the y values, 278 minus 130. Okay, and so for the x of the relative vector, we get minus 204 miles. All right, the y of the relative is 12 minus 216i plus 278 minus 130j, and dotted with j, so it's really just this term, and so we get 148. So we could have skipped the dotting part. We could have just taken this term for the y, this term for the x, and it would have been the same thing. So x is minus 204, which is from this term. Y is 148 from this term. By taking the entire vector and dotting with j, we get projections, and that is formally how we get that. But you could use your intuition to just say that the y value is just the difference in the y's for each vector. All right, we have one more part to do here. The position of this midpoint relative to the origin. Okay. So the way we set this up is we have a relative vector from m to I, and the vector from m to h is half the magnitude but in the same direction. So the vector of h relative to m is 1/2 the vector of I relative to m. So the vector of I relative to m is 195 minus 216 is the x component, 413 minus 130 is the y component. We calculate those and divide by 2. We get this for RHM, which is this vector right here. RM, it can just be written down from the locations of M. Okay, and so then we can get RH, which is what we're after, by summing RM and this relative vector RH slash M. Okay, so we just add the components here, okay, and we end up with 206i plus 272j, which is the xy components. X is 206, y is 272 for this vector right here. Okay. Now, one more units, one example on units. Okay, so suppose we have some string and it's just kind of hanging out there, and one end of it is moving at some velocity which is given, and we want to know the velocity of the string all along the string. So we have some coordinate s, which tells us where we are along the string. It's a distance. And then as a function of s and as a function of this initial velocity, we want to know what's the velocity of any point on the string. Okay, so since this velocity of the end is a function of time, then all these will be a function of time. So at any point on the string, the velocity will be a function of position, s, and time, t. So suppose somebody tells us that we can write the velocity of any point on the string as alpha plus beta t squared minus gamma s plus delta s over t. Question is, what are the units or dimensions of these constants, alpha, beta, gamma, and delta? And then if they're all equal to 1 in SI units, what are they in American units or British units? Okay, so it's pretty clear. Velocity has units of length over time. So alpha, since it has the same units as velocity, will also have length over time. And then each of these individual terms has to end up with length over time. So for example, at the end here, s is a distance, t is time. So we have to have the product delta times s over t. Sorry about that. We have to have that be the product of those three be length over time. So by knowing that this is length over time right here, it looks to me like delta is going to be dimensionless. All right, but let's work through it. So for the first term, alpha, as I said, must have the same dimensions as v, which is length over time. So now beta, for beta, the product of beta times time squared, or the units of that product, has to be length over time. So we say the units of beta, we refer to units in square brackets, times time squared has to be length over time. And then you can just kind of use algebra on this. So you divide by time squared. So the units of beta are length over time cubed. For gamma, the product of gamma s has to have the dimensions length over time. So the product, the dimensions of gamma, or units of gamma, times length has to be length over time. The lengths cancel, so gamma is 1 over time. And then finally, delta times s over time has to be the units of delta times length over time. And that has to be length over time. Lengths over time cancel, and delta is dimensionless. Okay. And then the second question is, suppose all these constants are equal to 1 in SI units. Alpha has units of meters per second. So alpha is 1 meters per second. What is it in the British units? Well, we have seconds are the same, but we have to convert meters to feet. So we have 1 meter per second times 1 foot per 0.3048 meters, and that gives us 3.28 feet per second, right? Feet per second is all that's left after we cancel the meters. And then beta is 1 meter per second cubed. So 1 meter per second cubed times a foot per 0.3048 meters. We cancel the meters. We get 3.28 feet per second cubed. All right. So if you're careful about units as we go through the semester, that'll simplify your life a lot. Be sure to keep track of units as you go through problems, and then make sure the units work out at the end, and that'll be a good check on your answers, and it's a good practice to just always check your units. All right, that'll do it.